I think we'll get started now. It looks like the attendees are slowing down here. So good morning, everyone. The recording has started and I think we are ready to go. Welcome to today's webinar with Matt Jones. For those of you who I haven't met yet, my name is Jessica and I'll be facilitating today's webinar titled Optimizing Completion Designs in Powder River Basin from Matt Jones, back for a second week in a row from Oxy. Thank you, Matt. Before we go into the presentation, however, I'm just going to go through a few meeting logistics. First off, as you all probably noticed, you are muted as we had over 300 people register for today's session. We're going to break into two parts. The first will be about a 40 to 45 minute presentation from Matt, followed by a 15-minute question period. Feel free to use the Q&A chat box to enter all your questions, or you can email myself at jessica@whitson.com. This webinar itself is facilitated by us here at Whitson. If you don't know Whitson, we are a shop extremely passionate about everything petroleum engineering, from our software platforms, Whitson Plus and Whitson PVT, to all of our training and educational courses. We actually just added a few more courses to our site yesterday, so feel free to take a look at whitson.com/training. And as always, these courses are complimentary for Whitson subscribers. You will actually now see a separate registration link that I've added on there for these courses. So if that applies to you, feel free to go in and register yourself for these courses. Now over to presenter Matt Jones. We are fortunate to have him here for a second week in a row. Texas A&M alumni. He spent the last 15 years with Anadarko and then Oxy. Has an immense amount of experience with fracture modeling, defit design, completion design, and advanced downhole diagnostics. So over to you, Matt.
Right. Thank you, Jessica. Let me share my screen here. Okay. And if you could let me know when you're able to see it. All right. Good morning, everyone. Hope your day is off to a good start. This morning, I'm going to be sharing with you a presentation that I actually gave at the Hydraulic Fracturing Technology Conference in Houston back in February. This paper and this project share the results of a very successful design of experiment that Oxy executed in Powder River Basin in 2023, where we were predominantly focused on evaluating and optimizing completion designs, specifically in the Niobrara Formation, using a myriad of different diagnostic data sets. Now, before we really begin the presentation, I think it's important to highlight some of the primary motivations behind this work and some of the key observations that were made along the way. First and foremost, we wanted to evaluate SDE, or Stimulation Distribution Effectiveness, of different stage designs. Now, this was done, as you'll see, through a very robust design of experiments with isolated completion design variables, and we were mainly focused on increasing stage length while maintaining treatment uniformity. The main idea behind the premise of being able to complete horizontal wells with fewer stages, save on cost, while hopefully maintaining a similar production response. Now, in this regard, what we saw in this project is very similar to what we've seen in other similar tests executed in different basins, different formations, and that is that rate per cluster, or RPC, and perf orientation are primary drivers of SDE. Generally speaking, designs that provide a high rate per cluster value tend to outperform designs that provide low rate per cluster values. And at the same time, designs with high side perforations, meaning perforations shot towards the upper half of the casing, tend to outperform designs with perforations shot towards the lower half of the casing. Another motivation of this work is that we wanted to test single perf and multi-perf cluster designs. So as the names indicate, the fundamental difference is with single perf clusters, you have a single perforation with a slightly larger diameter. With multi-perf clusters, you have multiple perforations per cluster with a slightly smaller diameter. Now, depending on the perf size, the amount of perf friction pressure between both designs can be kept similar, but it's a fundamentally different type of perforating strategy. So the way we did this was by keeping all other stage configuration variables consistent. And the reason we wanted to do this is that success had been reported in other studies that utilized single perf cluster designs with big hole perfs. Now, what we saw is that better SDE can be achieved with single perf cluster designs relative to their multi-perf cluster counterparts. And our numbers from this test indicate that that could be by as much as 40% or more, provided the conditions are correct. One of the issues we currently face, both I think within Oxy and within the industry right now, is that shaped charge options for big hole perforations are currently limited. There is some work being done with bullet style perforations that give you better consistency compared to shape hole charges, but that's kind of beyond the scope of this presentation. But that is an issue we're currently facing with full-scale implementation of that type of design parameter. Lastly, this kind of goes without saying, but I'll say it anyways. We wanted to utilize a variety of different diagnostics. Main reason for that is just to ensure that we collected enough information to inform future decisions. What we saw, and as you'll see in this presentation, is we actually have very good alignment between all diagnostics that were collected in this project. And so this gives us a high degree of confidence in design decisions moving forward. Just to provide a little background on the project, as I mentioned on the title slide, this test was executed in Powder River Basin in Wyoming in 2023, and it was done as a joint effort between Oxy and the Enhanced Oil Recovery Institute of Wyoming, or EORI. We had 4 primary wells that were completed in the Niobrara B bench and 1 additional well completed in the Turner Sandstone. In terms of frac order, the N5H, N8H, and T1H on the eastern half of the pad were completed first, followed by the N1H and the N3H. In terms of completion diagnostics, the N5H well is the well that had permanent fiber optics installed, and it also had acoustic perf imaging data collected post-frac. The N3H well is the well that had a disposable fiber optic cable installed prior to frac start of T1, N5, and N8H. Now, as you can see on the bottom left half of the slide, we do have a very exhaustive data collection program for this project. But just in the interest of time, and really what we spend the most time focusing on in the paper is the results from permanent fiber optics, disposable fiber optics, and acoustic perf imaging. This slide provides a ton of information regarding the completion design of experiment. As I mentioned earlier, our primary focus was on increasing stage length while preserving, or if possible, enhancing SDE. And again, the main idea behind that is just being able to complete a horizontal well with fewer stages while maintaining a similar degree of treatment uniformity, which should, in theory, lend itself to a similar or slightly better production response. We did intentionally keep certain variables consistent in this test. We kept cluster spacing and treatment rate consistent for all designs that were tested. We also kept the volume of sand and fluid per cluster consistent. So this is not a test on cluster spacing or stress shadowing. It's also not a test on volumetrics. The base design we had for the project is called in the paper and in this presentation Design A, which I'm showing here. Just to walk through it, it is an 8 cluster stage with 31.3 feet cluster spacing, which gives us a stage length of approximately 250 feet. 3 perforations per cluster, which gives us 24 total perforations per stage, and an advertised perf diameter of 0.45 inches. Also happens to be a geometric design, meaning it's not tapered, which implies that you don't have different numbers of perforations in heel clusters versus toe clusters. Beneath this, I have several calculated variables, which we'll look at later in the presentation. But for design A, it has 12 barrels per minute per cluster, 4 barrels per minute per perf, calculated an initial perforation of 2140 PSI. For this test, we did have a control stage, which is design M. This is a 6 cluster stage, same cluster spacing, but shorter stage length, 188 feet. Same number of perforations per stage, but 4 perfs per cluster as opposed to 3. Now, based on other tests we've executed, the expectation by including this design is that it would perform better or generate better treatment uniformity than design A, mainly because it's a shorter stage length and it has a higher rate per cluster value. So this design was meant to be a control. 2 pairs of designs to draw your attention to are C and D. We'll consider those to be pair 1, and G and H, which we'll consider to be pair 2. Pair 1, both designs are exactly the same in terms of architecture, with the exception of the perforating strategy. Design C is a multi-perf cluster design with 3 perfs per cluster. Design D is a single perf cluster design with 1 perf per cluster. So design C, the advertised perf diameter is still 0.45 inches, whereas for design D, it's larger, it's 0.62 inches. Pair 2 is G and H, so slightly longer stage length than pair 1 because we have 2 additional clusters. Both of these are 12 cluster designs, 375 foot stage length. G has 2 perforations per cluster. H has 1 perforation per cluster. So you can see with pairs 1 and 2, we're trying to hone in on what is the impact of doing a single perforation per cluster as opposed to multiple perforations per cluster. really trying to understand how does that impact treatment uniformity. Also, at the same time, increasing the number of clusters per stage, increasing stage length, and decreasing rate per cluster. Design I is the most aggressive design we tested in this project with 13 clusters per stage length just over 400 feet. One of our goals for the project was to have at least 3 analyzable stages per design, just to provide a certain level of confidence in the interpretation of results. We also alternated the design sequentially throughout the lateral from toe to heel, which I'm showing you here. This was done to minimize any impacts of geologic differences across the lateral going from toe to heel. You can see that there is a bit of faulting in the Niob where this particular well was drilled, but by and large, most of the stages are within the intended target formation. Now, as most of you know, when you install permanent fiber optic cable integrally with production casing, it tends to form a bit of a spiral pattern going from toe to heel. Because of this behavior, it is absolutely critical that the orientation of the fiber optic cable be mapped prior to designing your perf plan for the well. So in this plot on the left, I am plotting measured depth on the x-axis, heel closer to the left, toe closer to the right. And on the y-axis, I have orientation looking downhole. So it's plotted as though we're standing at the heel of the well looking towards the toe. It goes from 0 to 360. 0 and 360 both coincide at the top of the borehole. 180 is at the low side. So as you can see, from toe to heel, we have slightly less than 1 revolution for the fiber optic cable, which is fairly benign. This is actually somewhat advantageous for planning your perforations. You can have a certain degree of consistency with it. Worst case that I've personally seen is, I think it was 6 wraps on another well, which can definitely complicate your perf orientation planning. The other thing that we did prior to frac on this well was we collected a USIT with ISO scanner. So it's basically a CBL on steroids, giving us some kind of an indication of what the cement bond quality is throughout the lateral. And that's shown here beneath the orientation map. And you can see that we have slightly better bond in the toe than in the mid and heel portions of the lateral, but it's not anything to cause concern. This is pretty typical for other wells that we've scanned. Now, in terms of the perf orientation, there's several ways this can be done. One of the more recent advancements and what more operators have started to gravitate towards is internal orienting devices, meaning that the charge carrier within each perforating gun is independently oriented relative to other guns within the string. This gives you several benefits. One is just the independent orientation, meaning what one gun does doesn't necessarily impact another gun. The other benefit is that it has far less contact points relative to eccentric weight bars. Eccentric weight bars are a little bit more of an older technology. That being said, our experience with permanent fiber optic projects is largely based on the use of eccentric weight bars. Main reason for that is it gives you more QA/QC opportunities on surface when the guns are set up and run down hole. You're able to visibly see where your perforations are oriented relative to the tops of your eccentric weight bars. So there's a little bit more control in that regard. So we used eccentric weight bars for this well, built a customized perforating plan for every stage where we do account for gun eccentricity, meaning horizontal wells, guns lay on the low side of the casing. There is a difference between your gun orientation and your planned perf orientation. We did keep perf orientation consistent between all clusters and stages. There's a tremendous amount of risk and human error involved if you try to plan certain perfs within your stage at different orientations relative to others. So we just eliminated that. So every perf for a stage is shot at the same orientation. Also, no phasing between perforations, meaning they're all shot in a line. And as I said, eccentric weight bars instead of internal devices. Now, when you execute a permanent fiber optic project, it's inevitable that you're going to run into operational issues that complicate data analysis. So on this slide, I'm showing you a couple of examples of what we encountered when we were fracture stimulating the N5H well. Now, if we look in the top left, we'll just get oriented on what data I'm showing here. The top image is the distributed acoustic sensing, or DAS, waterfall plot, which, if we think about it from a y-axis, x-axis standpoint, your y-axis is depth. So you're closer to the heel at the top, closer to the toe at the bottom. The x-axis, as we progress from left to right, is time. So each one of these independent swim lanes is a cluster location, and the change in color is representative of the level of acoustic intensity that's occurring at that depth at that given time. So what you would hope to see is consistent swim lanes with similar levels of acoustic intensity throughout the entire stage. That would basically indicate that you've got more or less even treatment. Beneath that, we have our treatment plot, which has our basic treating data. So we have surface treating pressure, surface rate, surface prop concentration, bottom hole prop concentration. So we look at these two together to see what impacts we're seeing from a downhole perspective and what the corresponding effects are on surface. Now, this top image in the left is from stage 11, where we encountered a partial screen out. You can see that screen out start to develop in the DAS data at the toe end of the stage and progress uphole towards the heel. Simultaneously, as this is happening downhole, we can see an increase in surface treating pressure. And to ensure that we don't fully screen out and override the max allowable surface treating pressure for this casing design, we reduce rate substantially. So this gets us within pressure limitations, but you can see that it's only the 3 heelmost clusters that remain active for the remainder of the stage. So this is one of the stages that we would tend to throw out of the analysis because the final treatment uniformity is not necessarily a direct reflection of stage architecture. There's an operational issue associated with it. The top right is an example of stage 12 where we encountered a mid-stage shutdown. We have to shut down for approximately 30 minutes to rectify a surface equipment related issue. Generally, when we see shutdowns like this in other fiber optic projects, we usually lose at least one, if not more clusters when we resume treatment. But what you can see here is that all the clusters actually regain and sustain activity for the remainder of the treatment. So this is a bit unusual compared to other projects we've executed. It's also a bit of a pleasant surprise. If we look at the bottom left image, this is for stage 14. It's another mid-stage shutdown, but this one is longer in duration. It's approximately 90 minutes. Yet again, we see that all clusters regain and sustain activity when we resume treatment. I will say that this is anomalous compared to other fiber optic projects I've executed in other basins. So it's possible that the Niobrara Formation in Powder River is a little bit more forgiving in this regard. Unfortunately, we did break the fiber optic cable during the treatment of stage 23. The conditions of the break were highly unusual. Usually when you execute a fiber optic project, if the cable is going to break, you usually get some kind of indication that something is wrong in either the DAS or the DTS, distributed temperature sensing data. When the cable broke, in this case, it occurred only 2 minutes after we got proppant on bottom. And I think at the time we only had about 8,000 pounds placed. So highly unusual as to why it broke. No good explanation. We do know, as you'll see later in the presentation from the acoustic imaging data, it didn't break because we shot the fiber optic cable or anything like that. So a little bit unusual, but certainly unfortunate. When you have a break happen like this, you can still collect fiber optic data for the remaining stages from the point of the break back towards the heel, but you lose any further data collection from the point of the break down towards the toe. The slide gives an overview of the execution and also our stage validation screening prior to actually analyzing the fiber optic data for treatment uniformity. We had 30 stages receive their design volume of proppant. 3 that did not. Those were stages 23, 24, and 25. 23, we stopped the treatment at the point the fiber optic cable broke to try to not further degrade the fiber optic cable, which at the point of the break is essentially unprotected. So we stopped that treatment as soon as the break occurred, or not long after. Stage 24 successfully perforated about 60% of the way through the treatment. Started seeing some anomalous behavior on the DAS data, decided to stop treating that stage just to prevent further breaks. 25, the cable broke on the final gun of the plug-in perf run. As you'll see in the acoustic imaging data, we don't think this is because the cable was directly shot. We think it's because the repetitive concussive force of those guns going off in close proximity to where the fiber optic cable broke. That's our current working hypothesis. We actually had fiber optic cable breaks on 26 and 27, again, during the final gun of the plug-in perf run for both of those stages. For economic reasons, we decided to treat stages 26 and 27. When it broke on 25, we were still trying to collect as much data as possible. So we decided not to treat that stage and further run the risk of additional breaks. In total, we have 25 stages that we deemed valid for SDE analysis. This table in the top right shows the stages that were deemed to be invalid. It's a mix of different issues. We have partial screenouts, mid-stage shutdowns, which I showed you on the previous slide, fiber optic cable breaks, so stage 23 during frac, 25, 26, and 27 during wireline. We also had one stage that showed a meaningful level of communication between stages, likely culprit of that being poor plug isolation. Now, the reason I say that that's interesting is because in this project, we were using 100% dissolvable plugs. And what we've seen in other projects where we compare composite plugs to dissolvable plugs, we generally see better performance with composites. There's other parameters that go into it, not just is it composite or is it dissolvable. But it was definitely a pleasant surprise to see only one stage have questionable plug isolation. The rest of the stages looked as though they had phenomenal isolation. Okay, so now we're going to get more into the analysis of data and what's the interpretation of which designs and which design parameters perform best. Two parameters that we look at for virtually every project we execute like this are rate per cluster and rate per perf, or RPC and RPP. The two uniformity metrics we're going to look at to try to evaluate these two parameters are PDM, or proppant distribution metric, and PUI, or proppant uniformity index. PDM is the minimum to maximum ratio of proppant percent allocation among clusters in a stage. So it's not a straight volumetric calculation, it's a percent allocation. And those percent allocations are calculated using proprietary algorithms using the DAS data. PUI is a similar calculation, but it's 1 minus standard deviation over mean. Standard deviation and mean, again, applied to the proppant percent allocation among clusters in the stage. Now, let's look at rate per cluster first. So two plots over here on the left half, both have rate per cluster on the x-axis going from low to high. This left plot has PDM on the y-axis from 0 to 1, 0 being horrible treatment uniformity, 1 being perfect treatment uniformity. The left plot has PUI on the y-axis, again, 0 to 1, 0 being horrible, 1 being perfect. Now, what we can immediately see from both of these plots is that we have positive correlations between rate per cluster in PDM and rate per cluster in PUI. So essentially, the higher you get your rate per cluster value, the better your treatment uniformity should be. Now, there's a couple outliers we have to address, and both trends are very similar. So let's just look at rate per cluster versus PUI. We have 3 outlier stages for design I, shown here, which have low rate per cluster and high PUI. We also have 1 outlier for design M, which is our shortest stage length that we treated, that has high rate per cluster, yet low PUI. Now, to explain why these outliers exist, we need to look at perf orientation. We'll do that on the next slide. And before we move, let's look at rate per cluster versus uniformity. So very similar plots on the right half of the slide. We have rate per perf on the x-axis from low to high. Left plot is PDM on the y-axis. Right plot is PUI on the y-axis. Now, generally, we can use rate per perf as a proxy for initial perf friction pressure. The higher your rate per perf, the more perf friction pressure you have, or the more limited entry you have. That's true when you're working with multi-perf cluster designs that have the same perf diameter. However, remember in this project, we do have some designs that are single perf with a different or larger perf diameter. So rate per perf may not be the best proxy for perf friction pressure here, but it's still something we look at for most projects. And what you can see is that we have a negative correlation for rate per perf and PDM, but a positive correlation for rate per perf and PUI. So we're lacking directional alignment with respect to this particular parameter. Now, as I said on the last slide, we have a couple of design outliers when we look at rate per cluster versus PDM or rate per cluster versus PUI. Before we address those outliers, let's just take a look at what the treatment uniformity is as a function of perf orientation. The left plot is perf orientation on the x-axis from 0 to 360. Again, 0 and 360 both coincide at the top of the borehole. 180 is the low side. So 0 to 90 is upper half, 90 to 270 is lower half, and 270 back to 360 is upper half. So here we have PDM on the y-axis, same plot over here, it's just PUI on the y-axis. They're similar, so let's just focus on this plot, perf orientation versus PUI. Now, what we can see, regardless of design type, is that designs that are perforated in the upper half of the casing tend to generate higher uniformity compared to designs shot in the lower half by about 11%. Now, when we look at those outliers, let's start with design I, the longest stage length treated with the most number of clusters. All 3 of the designs that are included in the analysis were perforated in the upper half of the casing. Every other design in the analysis has at least 1 stage perforated in the lower half of the casing. So design I is biased from a perf orientation standpoint, and the single outlier for design M was perforated in the lower half of the casing. So this helps explain why we're seeing those outliers when we think about rate per cluster versus PUI and not seeing what we would expect. Now, if we look more at a design level, I have a couple of bar charts here on the right half of the slide. I've got average PDM by design type, so PDM on the y-axis, and I have average PUI by design type, PUI on the y-axis. Again, the trends are pretty similar between both, so we'll focus more on the PUI plot. Now, as we move from left to right in this plot, we are increasing stage length and also increasing the number of clusters per stage. So fundamentally, we're decreasing rate per cluster. Now, hypothetically, based on what we've seen in other projects that are similar, we would expect, as we move from left to right, to see a degradation in treatment uniformity. So when we go from design M to design A, we can see that drop off. Design A to C, where we add 2 clusters, so we go from 8 clusters to 10. We have a similar level of performance, so we don't necessarily see the drop in C as we would like to see, although we do see that going from A to C when we look at PDM. When we look at pair 1, C versus D, we see an uplift in treatment uniformity. And remember, the only difference between design C and D is the perforating strategy. C has multiple perforations per cluster. D has 1 perforation per cluster. So we see an uplift strictly as a function of changing our perf strategy. When we go from pair 1 to pair 2, we can see a drop off just categorically in uniformity. But again, when we make the change going from multiple perforations per cluster to a single perforation per cluster, we can see another uplift. Design I is just the unfortunate outlier, which, as I just told you, it's biased because it is the only design that has all of its stages perforated in the upper half of the casing. Every other design has at least 1 stage perforated in the lower half. Just to be fair, when we look at PDM, we do see the uplift going from C to D, but we don't necessarily see the uplift going from G to H. So if you consider 4 possible outcomes, pair 1 and 2 for PDM and pair 1 and 2 for PUI, 3 out of 4 times, it's indicating that going from multiple perforations per cluster to a single perforation per cluster gives us better treatment uniformity. When we look at the strength of correlation between average rate per cluster and average PDM or average rate per cluster and PUI, we can see that with all designs included, the strength of correlation is still quite strong. When we omit the outlier for design I, just because of perf orientation bias, we can see that the strength of correlation effectively doubles. So we know several things at this point. We know that designs that generate higher levels of rate per cluster tend to generate better treatment uniformity. And we also know that designs perforated in the upper half of the casing tend to outperform designs in the lower half of the casing. So perf orientation definitely matters. Moving out of the fiber optic data set, let's take a look at the acoustic perf imaging data set. So this data was collected on coil tubing after the post-frac cleanout was completed. We were able to successfully deploy the acoustic imaging tools to the toe of the well, and we were able to collect measurements for 735 perforations. In this data set, we did collect perforation entry and exit hole measurements. Entry hole measurements are on the inner diameter of the casing. Exit hole measurements are on the outer diameter of the casing. And down here, I've got a couple of examples of what these measurements look like or what the perforations look like. So this is just an example of a perforation that has been very slightly eroded or not eroded at all. This would be a perforation that has achieved what we would consider to be stable growth. This is a perforation that has fallen into the runaway growth category. In the presentation that I gave last week in the other SPE paper that we published as part of HFTC, we really get into the nitty gritty of what do these measurements mean? What can they be used for? So we're not going to really dive into that for this presentation. I'm just giving you an indication of what these measurements look like. Now, in terms of data quality, what we would hope is that all perforations fall into the entry plus exit category. They have all the necessary measurements to compute perf tunnel volume. So in this bar chart over here on the left, I'm showing you the perf measurement type by stage design. And what we would hope to see is that all of these green bars would be 100%. That never happens. You always have some level of occlusion with your imaging for various reasons. Most of the designs have close to 90% of perforations in the entry plus exit category. The only design that might be a little bit biased in this regard is design G, which has 73% of its perfs in the entry plus exit category. All the other designs are pretty similar. Now, in terms of where these perforations are located, as I mentioned earlier, we intentionally tried to perforate the upper half of the casing where the fiber optic cable would let us. So most of the perforations are located in borehole sextant 1, which is towards the top. The rest of the perforations are spread fairly evenly throughout the other borehole sextants. And just to get everybody oriented, sextants 1, 2, and 6 constitute the upper half of the borehole. Sections 3, 4, and 5 are all lower half. This plot over here on the right shows measured depth on the x-axis, heel to the left, toe to the right, versus orientation from 0 to 360. It shows the approximate location of the fiber optic cable relative to where the perf orientations were measured acoustically. So these are not planned perf orientations. These are where they were actually found to be. Now, we had fiber optic cable breaks on stages 23, 25, 26, and 27, which I've highlighted here. As you can see, there's no reason to believe that the perforations directly contacted the fiber optic cable. So the reasons for the break are really inexplicable. It's possible there was some type of defect that eventually just gave up on the treatment of stage 23. The fiber optic breaks on the perforating runs for 25, 26, and 27 may just have been from fiber embrittlements combined with concussive forces of those perforating guns going off repetitively. Okay, so comparing the results between acoustic perf imaging and permanent fiber optic results. On the left, I have the results from volumetric perf erosion analysis. And again, the other SPE paper that we published and that I presented last week really goes into the details on how this is done. This is showing the calculated volumetric uniformity index from 0 to 1. So again, 0 being very poor, imperfect treatment uniformity, 1 being perfect. VUI is calculated as 1 minus standard deviation over mean, where standard deviation and mean are the percent of volumetric growth per cluster relative to the total volumetric growth per stage. Now, the reason I'm pointing this out is VUI and PUI are very similar metrics. So if there's any truth to these diagnostic tools giving you the same results, these are the parameters that you would most likely want to compare. When we look at the volumetric analysis or volumetric erosion analysis results, we see the same directional trend as we did with permanent fiber. So when we go from design M to design A, we see a bit of a decrease. A and C are very similar. For pair 1, C and D, we see the uplift going from multi-perf cluster to single perf cluster. Going from pair 1 to pair 2, we see the decrease again, but we see another uplift going from multi-perf cluster to single perf cluster. I is still a bit of an outlier. So directionally, it's exactly the same between the acoustic perf imaging results and permanent fiber optic results. Now, what this means for us as an operator is that we would make the same decision or interpretation of the data with each of these diagnostic tools independently. The benefit of acoustic perf imaging is it's a fraction of the cost relative to permanent fiber optics. Last but not least, we have the results from offset disposable fiber. So again, we had a disposable fiber optic cable that was installed approximately 6 days before frac start of the N5, N8, and T1H. So we are watching fracture-driven interactions on the N3H approximately 12 to 1,300 feet away from the N5H. In total, we recorded 32 fracture-driven interactions, 21 direct frac hits, 6 approaching fracs, meaning the fractures were detectable, but they didn't quite intersect the N3H, and 5 reactivations, which can come from either potentially poor plug isolation, but recall when I was going through the permanent fiber optic results, we didn't see any indication in DAS and DTS data that we had major issues with plug isolation. The other possibility is either fracture reorientation or possible cement bond degradation, which allows some level of backflow into previous stages. So this is what we saw in terms of FDIs. The approaching fracs are largely the result of a sealing fault system that is observed between the midpoint of both the N3 and N5H laterals. So you can see those here in this small inset image, and you can see that this is where most of those approaching fracs are occurring. So there's definitely some impacts of geology here. 2 metrics that we looked at to try to assess far field uniformity and well spacing are relative VFR, or volume to first response, and normalized event length. Relative VFR is the volume to first response. So that's the volume recorded during treatment when the first fracture arrival is seen on the offset well, relative to the total volume of clean fluid per stage. And recall that we kept proppant and fluid volume consistent among clusters regardless of the design. So we're normalizing by a fair metric here. What we see when we look at relative volume to first response is that our P50 value for the frac hits only is 27%. So said more simply, we're seeing the first fracture arrival on the offset well, 1,200 to 1,300 feet away at 27% of the fluid volume planned for that stage. So that's fairly early. When we look at relative VFR for frac hits plus non-arrivals, and we just give the non-arrivals an arbitrary relative VFR value of 1, the P50 value changes to 35%. So a P50 range of 27 to 35% of when we're seeing that first frac hit the offset well. Now, there's tons of things you can get into in terms of debating whether or not frac hits on an adjacent well are a positive or a negative. That's kind of beyond the scope here, but what it does indicate is one of two things. Either our well spacing may be a little bit too tight, or the treatment uniformity value for different stage designs is having an impact on when we're seeing that first frac arrival. If the completion designs are kept consistent throughout the lateral, this is a little bit more of a straightforward assessment when you think about well spacing implications, but with the variability we have in designs here, it's a little bit more difficult to interpret. So it's one of two possible explanations. When we look at offset well normalized event length, this is essentially the offset strain length seen on the offset well relative to the stage length on the treatment well. So again, it's totally debatable as to whether or not frac hits on an offset well are a positive or a negative. But if you are going to see frac hits, you can get a sense of far field treatment uniformity. If you had perfect far field treatment uniformity, then you would expect to have a normalized event length of 1, meaning the impacted length on the offset well is the same as it is on the treatment well. So you would assume or draw the conclusion that the fractures you're stimulating on the treatment well are all being relayed over to the offset well. There's a little bit of subjectivity with that, with disposable fiber, which has less resolution than permanent fiber, but it's still a good thing to look at for directional results. What we see is something similar to what we saw in both the permanent fiber optics and the acoustic imaging results. So M to A, we don't necessarily see the drop off. It looks as though it's somewhat similar, but when we go from C to pair 1, you can definitely see that drop off in what I would say is far field treatment uniformity. We can still see a very slight uplift going from multiple perforations per cluster to a single perforation per cluster. From pair 1 to pair 2, we see another drop off. Here, it is very subtle, but you can still see the very small uplift from going from multiple perforations per cluster to a single perforation per cluster. This is where I actually flips. So what appears as though it is good near wellbore treatment uniformity for design I may not necessarily translate to good far field treatment uniformity. So that's the only thing that's not necessarily aligned between the diagnostic tools. Just to recap, as I showed you, rate per cluster and perf orientation are both drivers of STE. Designs that generate high RPC tend to outperform designs that generate low RPC, and designs with high side perfs tend to outperform designs with low side perfs. We did see better STE with single perf cluster designs, but again, one of the issues that we currently face, and I'm sure others face that are interested in this type of design, is that shape charge options for big hole perforations are currently limited. One of the issues that I've seen with these types of charges is that they are not as consistent in terms of initial hole size. They tend to have a higher standard deviation compared to standard deep penetrator charges, which is what you would use for multi-perf clusters. So that's one of the drawbacks. And again, we did have really good alignment between all the diagnostic tools. We saw the same directional alignment between fiber and acoustic perf imaging, saw very similar trends using the offset disposable fiber. So this does give us a very high degree of confidence in design decisions moving forward. Big thanks to my co-authors on this paper. Would not have been possible without a monumental effort from the team that was focused on designing and executing this project. Also, big thanks to Oxy leadership for allowing us to publish and present this work. Big thanks as well to Wyoming EORI for executing this project as a joint effort with us. And I would absolutely be remiss if I did not thank the field personnel who helped effectuate these designs. There's a ton of work that goes into the planning, but it's all for naught without good execution. So huge amount of thanks to the field personnel and also our diagnostic vendors for helping us collect and analyze this data. With that, I will close and open up for questions.
Thanks so much, Matt. I don't see any questions in the chat box, but I did get 2 emails. The first question that I received was, you mentioned that you used dissolvable frac plugs in this project and that the isolation between stages was quite good. Is this common, or is there something particular about the plug that you used?
So that's a really good question. I would say that for other projects I've worked on, that is actually not common. But the reasoning behind that is more than just, is it composite or is it dissolvable? The dissolvable plug that we used in this project is very similar in form and structure to a traditional composite plug, meaning it's not small, it's quite long. It's also got an OD or an outer diameter that's close to casing drift. It also has a very long sealing element relative to other dissolvable plugs. It also happens to have top and bottom hold down buttons. What we've seen in other projects that have dissolvable plugs that are shorter, don't have an outer diameter as close to drift, and have a short sealing element length is that they don't tend to provide as good of isolation. So no, we don't always see good performance with dissolvable plugs, but we have seen good performance with dissolvable plugs that are similar in form and structure to your traditional composite plugs.
Awesome. Thanks, Matt. Another question just came through in the chat here. From Yuri. It says, Matt, any commentary on production results validating the frac metrics observations?
Phenomenal question. I don't have production metrics for this well. We can't do a simple RTA assessment on this well just because the completion variables were changed so much throughout the lateral. So the production performance isn't necessarily able to be correlated to, what did we change? Typically what we would do with a fiber optic project like this is we would come back during production and do DSS RFS analysis, which is distributed strain sensing Rayleigh frequency shift. That gives you micro strain measurements going from producing to shutting conditions, or from initial producing to time-lapse producing conditions, where you can see the strain change along the lateral. And you can use that to infer the level of production uniformity and try to correlate that back to stage performance or different design parameters. But in this case, we lost the fiber optic cable. We had about a third of it remaining. So when you think cost versus value, how much is it going to cost me to go out there and do the DSS RFS assessment versus how much data am I going to get? We didn't think that we would get good strength of correlation. The alternative in this project would have been to run a conventional PLT, but the cost of doing that would have been quite expensive, and you're only going to get a single time lapse. So you'd only get one point in time of how is that well producing. You would have to spend additional dollars to go get multiple measurements. So unfortunately, I don't have production metrics here. I will say in other tests where we have done DSS RFS and we've managed to preserve the fiber optic cable, we see really good correlations between treatment uniformity and production uniformity. So we're firmly of the opinion that the better you make your treatment uniformity, the better your production response will be. We just can't necessarily quantify what's the point of diminishing returns.
Awesome. Thanks, Matt. Yuri, I hope that answered that for you. More questions are coming in here. So one more from email here. You showed how the rate per cluster tends to have a bigger impact than the rate per perf. Is this consistent with other projects that you or the Oxy team has executed?
I would say yes. Regardless of the basin that we're in, regardless of the formation that we're in, generally speaking, designs that have higher rate per cluster will outperform designs with lower rate per cluster. That is probably one of the, I would say, universal truths that I've seen from executing these types of projects. I have yet to see a project that suggests something like lower rate per cluster designs with higher rate per perf or higher perforation pressure will generate a better response. I have seen papers out there that speak to that. I just personally haven't seen that in the work that I've done in the projects I've been involved in.
Awesome. All right. Matt, you have one from a fellow Matt, Matt Hicks. He says, great presentation, Matt. Are you able to share learnings on production performance from the permanent fiber? Are they aligned with broad conclusions, or is there anything surprising?
Again, unfortunately for this project, we just were not able to do a production assessment. When we originally formulated this project, we had budgeted for doing DSS RFS interrogation post-frac, but just looking at how much fiber optic cable survived and the usefulness of the data that we were going to get, we just elected to not do it. This is one of those really unfortunate drawbacks of executing a permanent fiber optic project. And this is really one of the reasons why you kind of want to look at a diagnostic technology like acoustic perf imaging. It's very high reward, high risk. You're going to spend a lot of money to install the permanent fiber optic cable. If everything goes according to plan, you get really great data both during stimulation and production. If you break it, then some of that information unfortunately kind of goes out the window. Again, there's other things you can do. You can do conventional PLT, but it's quite expensive. It requires a downhole intervention, and you have to do it multiple times to make sense of the data.
Awesome. All right. So last question before we wrap up. I do know there's a few more questions here, and I will pass them along to Matt, and we can see if we can respond back to you in person or personally. So anyway, sorry, last question here from David DeWitt. Did all the stages have full design rate before the sand started?
That's a great question. I would say that the majority of them did. I can't quantify it for you, but when we were treating this well, we didn't have any rate limitation issues. There may have been a couple of stages of the toe that could have been slightly rate limited before we got proppant on bottom and started seeing some erosion and reduction of surface treating pressure. But I did not get the sense as we were treating this well that we were severely rate limited. There was very likely a general rate increase throughout the treatment of most of these stages, but it was certainly not like other scenarios that I've seen where, it's either a function of lateral length, tubular size, or perf architecture where you're severely rate limited. So that wasn't a big concern in this project.
Awesome. All right, more questions are coming in here. I apologize, guys. We are out of time, but I will make sure that we get responses back to you all. If you have any other questions for Matt, feel free to send myself an email, jessica@whitson.com, and I can facilitate getting responses back to you. And Matt, thank you so much for the presentation this week. We hope we have you again soon on our webinars.
Absolutely. I enjoyed it.
Thanks, guys. Thanks for joining, everybody. Really appreciate it. Take care.